This is question 42 of civil engineering paper of GATE 2017 forenoon session. Considering two axially loaded columns, namely 1 and 2, made of a linear elastic material with Young's modulus 2 into 10 to the power 5 megapascal, square cross section with side 10 mm and length 1 meter. For column 1, one end is fixed and other end is free. For column 2, one end is fixed and other end is pinned. Based on the Euler's theory, the ratio of the buckling load of column 2 to the buckling load of column 1 is. So, in this column, two columns namely 1 and 2 are given. The Young's modulus, the cross section and length of both the columns are same. For column 1, the end condition is one end is fixed and other end is free. And for column 2, the end condition is one end is fixed and other end is pinned. Now, we need to find the ratio of the buckling load of column 2 to the buckling load of column 1 as per Euler's theory. So, this question is from the topic of Euler's theory of buckling load of column. You may study about this Euler theory and for different end condition for the columns in lecture 37, a stability of columns 1, strength of materials by Professor S.K. Bhattacharya, IIT Kharagpur. So, one of the factor which governs the critical loading is this the end condition of the column. So, based on the end condition, an effective length is defined. So, there are four conditions here you may see in this table. There are four conditions are given, four end conditions are given, and the effective length corresponding to each conditions are also given in this table. So, now this critical loading can be found as pi square EI by LE square, where LE is the effective length of the column. Now, for in this question, we need to find the ratio for the column 2 to the column 1. So, for column 1, the end condition is for column 1, the end condition is one end is fixed and other end is free. One end is free and other is free. So, we may say that the effective length for this column will be one end is fixed and other is free. So, effective length will be 2L. So, the critical loading for this column will be pi square EI by LE square. So, pi square EI by effective length is 2L. So, 2L square. So, it may be written as 1 by 4 pi square EI by L square. Now, for column 2, the end condition is given in this question is the end condition is one end is fixed and other end is pinned. One end is fixed and other is pinned. So, for this condition, the effective length of the column will be L by root 2. So, for this condition, the critical loading of this column will be pi square EI by effective length square. So, effective length here is L by root 2 square. So, it will be 2 into pi square EI by L square. Now, we need to find the ratio of the buckling load of column 2 to the column 1. So, the ratio of this buckling load of column 2 to the column 1. So for column 2, the critical loading is for column 2, this is for column 1 and this is for column 2. So the for column 2, the critical loading comes as 2 into pi square EI by L square. And for column 1, the critical loading comes as 1 by 4 pi square EI by L square. So here this pi square EI by L square is common, so this will be cancelled out. So the ratio will come as 2 into 4, that is 8. So here we get the ratio as 8. So the ratio of the buckling load of column 2 to the buckling load of column 1 is 8. So here 8 is the correct answer for this question. Thank you.